In this video, we're going to discuss the differences between performing reactions with aldehydes and ketones versus carboxylic acids and their derivatives. You may recall from the aldehydes and ketones chapter that we learned about acyl addition, where you would react an aldehyde or a ketone with a nucleophile and it would add to the carbonyl carbon. When you do the same type of reaction with a carboxylic acid derivative, it is instead an acyl substitution mechanism, which is a nucleophilic addition followed by an elimination. So for example, in the compound below, we are assuming that we have an alkyl group where it says R, L stands in for leaving group, and the nucleophile is here and also has a proton attached to it. So the nucleophile would attack the carbonyl carbon and push the pi electrons from the pi bond up onto the oxygen, creating a lone pair. This creates what we call a tetrahedral intermediate, because remember an original compound would be sp2 trigonal planar. So by adding to the carbonyl compound and breaking the pi bond, putting those electrons up onto the oxygen, we've created a tetrahedral structure. Now this is not our final product, and we would also want to remove that proton before we moved further. So a conjugate base of something, which would be dependent on the reaction conditions, could deprotonate it. Now at this point in the reaction with an aldehyde or a ketone, we would protonate the oxygen and make an alcohol or a hydroxyl group, depending on what the nucleophile was. We saw something similar with the formation of cyanohydrins. In this reaction, however, we have something different. We have a leaving group. So instead of protonating the oxygen, we are going to reform the double bond between the oxygen and the carbon and kick out the leaving group. So this gives us our final substituted product. For an example, we're going to do a reaction between an acid chloride and water. So remembering that water can act as a nucleophile, the lone pair on the oxygen, or one of the lone pairs on the oxygen, is going to attack the carbonyl carbon, which pushes the electrons from the pi bond up onto the oxygen. This creates a tetrahedral intermediate in which we have a positive charge on the oxygen that just attacked the carbonyl carbon and a negative charge on the oxygen that received the electrons from the pi bond. Now in this next step, depending on what your leaving group is, you may do the two next steps in a different order, but in this particular reaction, we're going to reform the double bond and kick out chloride. At this point, the product would then be deprotonated by another molecule of water to give us our final product, which would be a carboxylic acid. Plus H3O plus chloride, our leaving group. Now, if you're wondering why chloride did not do the deprotonation, it's because you cannot create hydrochloric acid in aqueous conditions. They would eventually dissociate to H3O+ and chloride anyway, so we just showed the deprotonation with water. So the question becomes, why don't we do this elimination step with aldehydes and ketones? Why do we take this tetrahedral intermediate and protonate it rather than kicking out a leaving group? And the issue is just the identity of the leaving group. Imagine that the electrons in this molecule came down to reform a pi bond between the oxygen and the carbonyl carbon and kicked out this R group. This would give us a substitution product with the nucleophile attached to the carbonyl carbon. And an R group with a negative charge. So this would be a negatively charged carbon, a carbanion. If we did this with an aldehyde, we would be kicking out hydrogen, giving us the same substitution product and an equivalent of hydride. Neither of these are good leaving groups. These are both very strong bases and therefore horrible leaving groups. So this is why we don't kick them out. It's because they wouldn't leave even if we did that on paper. So this brings us to our next topic, the relative reactivities of acyl compounds. Now, from here on out, every time we look at acyl compounds, we'll always discuss them in the same order. We'll always look at acid halides, followed by acid anhydrides, followed by esters, and followed by amides. You may notice that nitriles are missing from this list. It's not because they don't count or because they don't do chemistry. It's that they're not as easy to compare since they don't have the carbonyl carbons. We can't do a direct comparison of acyl substitution to something that doesn't have an acyl group. So we are discussing strictly the acyl compounds that qualify as carboxylic acid derivatives. So the acyl chloride is more reactive than the acid anhydride, which is more reactive than the ester, which is more reactive than the amide. The question is why? And it turns out it's based on the identity of the leaving group. If we take a look at all the leaving groups that would be formed in an acyl substitution reaction with each of these, for the acyl chloride, we would be kicking out an equivalent of chloride. For the acid anhydride, we would be kicking out a carboxylate. For the ester, we would be kicking out an alkoxide. And for the amide, we would be kicking out an amide. In this case, this one is a very specific amide called azanide. Now, what do we know about these compounds? Because we've seen them all before, and we've discussed their leaving group abilities before. Which one is the best leaving group? Hopefully you're recognizing that chloride is the much better leaving group in this situation, and azanide is a really bad leaving group. But what makes them a good leaving group or a bad leaving group? What is the property that actually makes this decision for us? That has to do with their basicity. Chloride is the weakest base in the list here, whereas azanide is the strongest base. So we have to look at this as a question of stability. Is a reaction that produces a very strong base more favorable than a reaction that produces a weak and less reactive base? Not so much.